Welcome to the fifth AI project, our final bonus project. The purpose of this project was to design and implement a Sudoku solver using artificial intelligence techniques. Formulate Sudoku as constraint satisfaction problem using variables, domains, and constraints, and analyze different backtracking-based approaches and optimization techniques. We had to implement the most efficient approach based on the analysis, test the solver on Sudoku puzzles with different difficulty levels, and compare the algorithm performance using execution time and search efficiency metrics. Some of the key questions are: how can Sudoku be formulated as a constraint satisfaction problem? What variables, domains, and constraints define the Sudoku problem? How do basic backtracking perform when solving Sudoku puzzles? Which optimization techniques improve their solver efficiency? Some of the concepts include artificial intelligence, constraint satisfaction, search algorithms, backtracking, heurisms, optimization, problem-solving, computational efficiency, recursive search, and logical reasoning.
During these experiments, several important concepts related to constraint satisfaction problems were explored. Sudoku was treated as an AI search problem where each empty cell represents a variable. Each variable contains a domain of possible values from 1 through 9. And constraints prevent repeated values with rows, columns, and 3x3 subgrids. The project also studied constraint propagation using AC3, backtracking search algorithms, and heuristics such as MRV, LCV, and MAC. These techniques were implemented to optimize the recursive search process used to solve Sudoku puzzles. The information gathered from the experiment focused on how Sudoku can be modeled as a CSP, how constraints help reduce invalid possibilities, how AC3 preprocessing improves efficiency, and how heuristics like MRV and LCV help reduce search complexity. In addition, the project explored the relationship between puzzle difficulty and recursive calls, as well as how AI techniques can improve logical problem solving.
For the experiment setup, Sudoku was formulated as a constraint satisfaction problem, which each cell in the 9x9 grid was treated as a variable with the possible values from 1 to 9. The initial clues were represented as fixed domains, while empty cells were assigned domains containing all possible digits. The solver used an IMA Python CSP structure. The selected method combined AC3 preprocessing, backtracking search, MRV variable selection, the degree heuristic as a tiebreaker, list constraining value ordering, and a MAC propagation during search. And to evaluate the solver, there were 3 difficulties: easy, medium, and hard. This is that shows the Sudoku puzzle using experiment. The easy puzzle has more clue, while the hard puzzle has fewer force moves and requires more search. And this is the difficulty score to show that whether the solver only works on simple cases or it can also handle puzzles that need deeper backtracking. And this is for the solver results. All 3 puzzles were solved correctly. The AC medium puzzle was solved almost immediately after the AC3 propagation, which is why they only require 1 recursive call, 0 assignments, and 0 backtracks. Meanwhile, the hard puzzle required about 5 seconds, 13,020 recursive calls, 12,956 backtracks. This shows that AC3 alone was not enough for the hard case, so the solver needed to use backtracking with heuristic and MAC propagation. The figure 1 shows the runtime difficulty. A logarithmic scale was used because the hard puzzle took much longer than the easy and medium puzzles. Without the last scale, the easy and medium bars would be almost impossible to see. Meanwhile, the figure 2 shows the number of recursive calls. The easy and medium puzzles only require 1 recursive call because the constraint propagation already reduced the domains enough to solve them. The hard puzzle required thousands of recursive calls, which confirmed that it's the real stress test for the solver. Here for the backtracks, is that the number of backtracks. The easy and medium had 0. Meanwhile, the hard puzzle had 12,156 backtracks. The result makes sense because hard Sudoku puzzles are designed to avoid obvious force moves. The solver had to explore many possible assignments and reject invalid branches before finding the correct solution. Okay.
For this project, we studied how Sudoku can be solved using constraint satisfaction problem techniques in artificial intelligence. We explored concepts such as variable, domains, constraints, backtracking search, and heuristic optimization methods like MRV, LCV, and MAC. During the experiment, we observed how AC3 preprocessing and constraint propagation reduced invalid possibilities before the search even began. We also compared how the solver performed across easy, medium, and hard Sudoku puzzles. In conclusion, the project demonstrated that CSP techniques provide an efficient and structured way to solve Sudoku puzzles. The heuristic significantly improved performance by reducing unnecessary recursive calls and search complexity. Overall, this project highlighted practical applications of artificial intelligence and logic reasoning and optimization problems.
Lastly, for future work, there are several ways this project could be improved. One possible improvement will be comparing our selected approach directly with simpler methods, such as plain backtracking and forward checking only, in order to better evaluate performance difference. Another improvement will be expanding the experiment by testing multiple puzzles for each difficult level, instead of one puzzle per category. This will provide more reliable average results. Additionally, a strong global out-different propagator could be implemented, since our current solution uses binary constraints supported by AIMA CSP framework. For reference, our project was mainly based on artificial intelligence and modern approach by Rosa and Norvig, the AIMA Python project library, and the course materials from Econ 5015 related to constraint satisfaction problems. Thank you.